Today we're going to look at problem 3.44, which is a thermal resistance problem. It gives us a 3 millimeter diameter electrical wire with a 2 millimeter thick rubber insulation. It gives us the K value of that insulation and a contact resistance for the interface between the two materials. It also tells us a convection coefficient for the outside surface of the insulation and the ambient air temperature. It then asks if the temperature of the insulation cannot exceed 50 degrees C to find the maximum allowable electrical power that can be dissipated per unit length of the conducting wire. It also asks for the critical radius of the insulation.
All right, I have gone ahead and written out the given information for the problem. I got the contact resistance and thermal conductivity, that important max temperature, as well as those numbers for solving for the convection. And then I made a little schematic. You can see the wire here and the insulation. Those have their diameters and thickness. And then, of course, it's surrounded by air. I've also just written a little reminder so we make sure we remember what we are solving for. Of course, we're looking for the energy generation in the wire that allows us to stay at that 50 degrees C, and then also the critical radius of the insulation. What I want to do next is quickly draw a thermal circuit. I've gone ahead and drawn the thermal circuit here with the contact resistance, conduction through the insulation, and convection resistance into the air. And it looks like we would need to solve for 3 resistances. However, we are looking at the max temperature of the insulation, not of the wire. So the max temperature of the insulation would occur at that interface, but that means we're really looking at this temperature, not this one, which means we can just ignore that resistance. And so we actually only have to look at these two, which simplifies the problem a little bit for us. So let's go ahead and come up with an equation for energy generation using these two resistances. So solving for Q prime is actually pretty simple. It's just delta T over the sum of the resistances. Again, we are interested in the inside temperature of the insulation, so that will be here, not temperature of the wire. And then also, of course, the outside temperature. And then our 2 resistances for conduction and convection. So next I will expand out this equation, plug in some numbers, and we'll have an answer for energy generation. The next thing I did was expand these resistance equations. They are a little different than maybe when we are used to, because of course we're looking at a cylinder, so we get this funny natural log of the ratios of the radiuses. But these are those 2 equations expanded, and then down here I just went ahead and plugged in. So the temperatures, of course we're looking at that T max, and then the ratio of those radiuses, the thermal conductivity, outside radius, and convection coefficient. So plugging that whole big equation into a calculator will get you a final answer for energy generation of 7.37 watts per meter. So that is energy generation. So we'll move on to writing an equation for the critical radius of the insulation. So next we're finding critical radius. And in case you've forgotten, critical radius for insulation, or critical thickness for insulation, is the thickness of the insulation that is optimal. So whatever the critical radius is in this situation would be the optimal thickness of insulation that would allow the most energy generation while maintaining that temperature. So that's why it's useful for this problem. It is actually very easy to solve. It is just a ratio of the thermal conductivity to the convection coefficient, which means we already have everything and we can just plug in and get a number. Plugging in those two numbers gives us an answer of 0.0087 meters, which we can just convert to 8.7 millimeters, a little more relevant unit for the problem. And that means that the ideal thickness would be 8.7 millimeters. So as this 2 millimeter thickness increases to 8.7, this energy generation number would go up. If the thickness gets past 8.7, that energy generation would start going back down. So that is the problem finished. We have solved for energy generation and critical radius for this insulated wire.